Hello everyone and welcome back to our channel. Today we are diving into a classic LeetCode problem called longest repeating character replacement. What makes this problem special is how it challenges you to think strategically with the sliding window technique, a crucial concept in algorithm design. Mastering this problem will not only boost your problem solving skills but also give you a solid foundation for tackling more complex challenges in coding interviews. So let's dive in and crack this problem together. Alright, let's start by understanding the problem statement for longest repeating character replacement. So you are given a string s and an integer k. Your task is to find the length of the longest substring that you can create by replacing at most k characters in the original string. So the goal is to make this string contain only one unique character repeated multiple times. So you'll be provided with a string s and an integer k. And basically what you can do is you can choose any character of the string and change it to some other character. Okay, and you can perform this replacement operation in at most k times. That means in a string you can only change two characters to some other character. Okay, and you will have to return the length of the longest substring containing the same letter. Okay, so in any given string you will have to find such substring whose all the characters have the same value after making k replacement. Okay, so for instance here if you see, if I'll make I am allowed to make two replacement, right? I can't make more than two. So if I'll change this a and the third a to b, then all my characters would be b, and that would be the longest one. That's why output is 4. Okay, if you look in the second example, I can only make one character replacement, right? I can't make more than one. So if I'll change this middle a to b, then I will have b, right? So this will be 4. Or there can be multiple answers as well. In initial also you can see that if I'll change this b to a, then I will have a, right? So that will be the 4. The length would be the 4. Maximum I can change 1, and after changing 1 I can achieve the longest substring as 4. Okay, so our goal is to find longest substring out of all the substring in a string which has the same letter. Okay, so that's our overall problem statement. Now let's look at the approach to solve this problem. If I talk about the brute force approach, in the brute force approach what we can do is we can extract all the substring and identify which among these substrings are the valid one or meets our criteria, and hence find the longest one. So what we can do is we can slide through the window to find all the substring. So we can have a start pointer pointing to the first character, and then we'll keep on expanding our end character to find each possible substring. So initially it will be end here, and then next it will be here, right? Then first substring would be this one, second substring would be this one. Then we'll keep on expanding our end pointer to find the next substring. So we'll go ahead like this till here, and this will obviously cost me O of n, right? Or maybe I'm running a loop here, okay, where my end pointer is moving. Okay, and now this will give me all the possible substring starting from the first character. Now if I'll have to check other substring, so what I'll do after completing this, I will update my start pointer to here, and then again repeat the same process, okay, of moving the end. So this will give me all the substring starting from here. So that's why you can clearly see that there is a nested loop, that is initially moving the start pointer, and then and within that start pointer will move the end pointer. So this will cost me O of n square, okay, to find all the substring. Now next, within each substring, to check whether it is a valid substring or not, we need a maximum frequent character within this. that logic would cost me O of n time complexity at worst, because in worst case my substring can be the entire string. Okay, so we can clearly see that the time complexity of the brute force approach would be O of n square. Okay. So let's try to look an optimized way. Now let's look at the optimized approach. So in our optimized approach, we'll make use of a sliding window, and we'll see that the substring represented by that sliding window is a valid one or not. If it is valid, then we'll try to expand the sliding window, because our aim is to find the longest one. Okay. And if the substring is not valid, that is within the sliding window, I have to replace more than k characters to make it valid. Then what we'll do, it will be an invalid one, and we'll try to shrink it. We'll move our left pointer as well from here to here, and we'll shrink it. So our new substring would be this one. Okay. So we'll use this technique to find whether each substring is a valid one or not, and if it is a valid one, then we will update our longest value. Now what would be our criteria to check whether it is whether the substring that we are sliding is a valid one or not? What we'll do is we'll maintain the maximum frequency of any character within that sliding window. So for example, here you can see that our maximum frequency of character within this sliding window is from A, and it is 3. Okay. And why we are doing this, that when we subtract this number from the sliding window, main sliding window, then whatever the number we'll get, that will be the replacement allowed within that sliding window. So here, if I'm subtracting 4 minus 3, that means I have to replace only one character, which are the less frequent one, B. Okay. So let me ask you a question. In this substring, which one should be removed to make it valid and the longest one? Obviously the less frequent one, right? I'll not remove A, because if I'll remove A here, then to make it identical, if I'll remove A and replace it with B, then to make it identical, I'll also have to shrink, and my longest would be this much only. Okay. So instead, what I will do is I will remove B and make it A, so that I don't have to shrink, and this would be my longest one. Okay. So this is the key idea behind this. So in each sliding window, we'll also maintain our maximum frequent character, and we'll try to check our whether it meets our criteria or not. That is how many number can we replace, and this number of replacement is less than or equal to k or not. Okay. And we'll make use of a frequency dictionary or a hash map to maintain the frequency of character within the sliding window, so that we can track our maximum frequent character. Let's try to understand this with an example. It will be much easier if we do that. So to maintain sliding window, we'll have two pointers, that is start pointer and end pointer, and both will be pointing at the beginning of the string initially. Okay. And in each iteration, we'll expand our sliding window, so our end pointer will move, and at any point of time, if it becomes invalid, then we'll also move our start pointer by shrinking the sliding window size. Okay. To simplify our overall process, we'll make use of these 4 steps in each iteration. Okay. First, we'll update our frequency. That is, initially when end pointer is pointing here, I'll update my frequency like this. So currently only A is encountered, so A is 1. Okay. And I'll count the maximum frequent character. So my maximum frequent character till now is just 1. And now I'll find the replacement needed. So initially we don't need any replacement, because 1 minus 1 is 0 and it is less than 1. So there's no question of invalid. And also in each iteration, I will maintain my longest substring, that is the current sliding window. Current sliding window is of size 1, so it will be 1. Okay. So in next iteration, I will move this end pointer here, and I will see that it is 2, and I'll update the frequency. So I have updated the frequency, and I'll find the maximum frequent character. It is 2, Now I'll find the replacement needed. So to find the replacement needed, I will just subtract this 2 from my sliding window. Sliding window is of size 2. 2 minus 2 is 0, is still less than or equal to 1. So it is a valid one. So finally, I'll update my longest. Okay. So in next iteration, I'll move this end pointer here. In this, I'll update the frequency of the new character. New character is B. So next I will count my maximum frequent character. Maximum frequent character is still A, that is 2, and I'll find whether the replacement is needed or not. So in this case, my sliding window is of size 3, and 3 minus maximum character 2 is 1, right? This 1 is still less than or equal to 1, so it is a valid one. So I don't have to check this, and my longest becomes now the size of the sliding window, that is 3. Okay. Similarly, I'll move this end pointer here, update my frequency. Okay. Now count the maximum frequent character. Maximum frequent character is A, that is 3. It will be 3 now, and I will check whether the replacement is needed or not. So now my sliding window size is of 4. So 4 minus maximum character is 3. 3 equal to 1. So this is also a valid one. So I don't have to shrink, and I'll update my longest to 4. Longest sliding window is 4 till now. Okay. Now next iteration, when I expand my sliding window here and I'll get new character is B, I'll first update. And what is the maximum frequent character? Maximum frequent is still A, that is 3, but now my sliding window is of size 5, right? So when I try to find whether the replacement is needed or not, that is size of the sliding window minus maximum 3 would be 2. So 2 is not less than or equal to k. So it becomes greater than k. That means I'll have to replace 2 characters, which will make it invalid. So when it is invalid, what we'll do is we'll shrink the window, that is remove the old character. So in this case, what we'll do is we'll move our start pointer from here to here, and we are shrinking it, right? Initially, earlier it was of size 5, now it is 4. Okay. After shrinking, we'll update our frequency here. A becomes 2 now. Now here, after I have decreased the frequency of A from 3 to 2, you might have questioned that we should also update our maximum frequent character, because now earlier it was 3, now it has been reduced to 2. So to maintain correctness, you can obviously do it, like you can iterate through the frequency and then check which is the maximum now, but that will cost you O of 26, right? Because maximum you can have from A to Z, all the alphabet, and iterating through it will cost you O of 26. You can obviously do that, but even if you don't do that, it will not affect our correctness. It will rebalance it, so you don't have to worry about it. It will always give you the reliable. In that way, I'll just update our maximum character till now, so I don't have to recompute by going through the frequency and finding the maximum frequent characters. It will make our algorithm a more performant one. Okay. So now in next iteration, our end pointer will move here, and it sees what is our maximum frequent character. Earlier it was 3, but now again it will become 3, because when we have encountered B, we'll update our frequency, right? So now my B's frequency is 3. Now I'll count the maximum frequent character. Earlier we have not reduced it to 2, so we have say 3 only, and our current frequency is also 3. So it will be 3, and find the replacement needed. So my sliding window is again it's 1, 2, 3, 4, 5, and sliding window minus maximum is equal to 2, so which is again not a correct substring. It's not a valid one because it is greater than k. So we'll have to shrink it once again. So we'll shrink by moving this start pointer here, You know that if it's an invalid replacement, that is after shrinking, we'll remove the old character, that is A. So I'll update the frequency of A here. My current sliding window is of size 4, so I don't have to update it, it's already 4. So this is done. Now in next iteration, I will move my n character once again, try to expand the sliding window. New character is A, so frequency of A is increased once again. Maximum frequent character was of B3, and I'll check whether the replacement is needed or not. Current sliding window is 1 2 3 4 5 5. 5 minus 3, the maximum one, 3 is equal to 2. Again, it's an invalid one. So I will try to shrink my sliding window by moving the start pointer, and current sliding window is 4, so longest is 4. Okay. So this is the overall logic to solve this problem. In each iteration, after performing these steps, we are tracking our longest. So finally, we'll return this longest as a result. Talking about the time complexity, in each iteration, we're just processing each element. That is, each character will be processed just once. So end pointer will keep moving forward, and sometimes start pointer will also move forward. So overall, our time complexity would be O of n, because each element will be processed just once. And talking about the space complexity, we are maintaining a dictionary or hash map of frequency, and the size of this frequency at most can be of 26, because we can fit 26 alphabets within this, A B C D to Z, right? So our space complexity is O of 26, but we can count it as a linear one, and we can say that O of 1, right? Because our space complexity is a constant value, that is 26. So that's why our space complexity is O of 1 and time complexity is O of n. Okay. So that's our overall approach to solve this problem. Now let's look at the coding. Let's start with the coding. So initially I'll have an n, which will be the length of string, and then I need the result to be stored in longest substring. Okay. Initially it will be 0, and then I'll also have to make use of maximum character frequency. So initially it will be 0. I need a frequency dictionary to maintain frequency of characters within the sliding window, and for this I'll make use of default dict, which I have imported here, and with the help of default dict I can get the initial value as 0 by default. So now I also need a start pointer, which will be pointing to 0, and I will iterate the end pointer till the end. Now in each iteration, we'll perform all these steps, right? So we'll perform these steps. So initially I'll update my frequency, that will add the frequency. So my frequency, I'll get it from here, and so it will be s of end, right? So that will be the alphabet pointed by end pointer. So I'll have to update this frequency, that is adding it, and then I'll have to find a maximum character of the sliding window. So to find the maximum character of the sliding window, we'll just update our maximum character if we have found the new frequency as the greater one. So I'll just make use of max, and if the new frequency is greater, then we'll update it. Okay. Now we'll check if the replacement is needed or not. So to check it, I'll see what that the size of sliding window minus the maximum character is greater than k or not. If it becomes greater than k, that means the number of replacement becomes greater than k, then it is invalid, right? If it is less than or equal to k, then it is fine, but if it is greater than k, then it will be an invalid one. So size of the sliding window minus maximum character will give me how many replacement we can make in that sliding window, right? If it is greater than k, then it is an invalid, and if it is invalid, then we'll have to shrink the window. To shrink the window, we'll first remove the frequency as start, right? Frequency by 1, and also update our start pointer. We don't have to reduce our maximum character. I'll update our longest substring, that is even with shrinking or without shrinking, what is my current valid sliding window. So maximum of earlier value and the new value, that is end minus start plus 1. Okay, so if my current sliding window is greater than the previous one, then that will be the longest substring. So that's it. So finally we will return our longest substring as a result. Okay, let's run this code now. Cool. Now let's submit this. Super. And that's how we efficiently solve the longest repeating character replacement problem using the sliding window technique. By applying this approach, we achieve an optimal of O of n time complexity, making it an ideal solution for handling large strings in a coding interviews. If you found this video helpful, please give it a thumbs up and subscribe to our channel for more coding challenges and interview tips. And don't forget to hit the bell icon to stay updated with our latest uploads. If you have any doubts or suggestions, feel free to leave a comment below. I would be more than happy to assist. Thanks for watching, and I'll see you in the next video.